Alright, so this is lecture 2. I'm going to dive straight in. First of all, let's define Rn. Rn, of course, is, well, it's R cross R n-fold times, where n is a positive integer. Now, our typical choice of notation here is a little bit different than what you might have seen in Calc 3 or multivariate calculus. So we're going to use these so-called contravariant indices for our space here. There are other reasons that we'll see why we're doing that as we go on here, but in short, the p upper I, well, they're just real numbers, all right? Of course, Rn permits, there's obviously a vector space structure here. If we have p, 2 points, p and q, and you want to add them, you can define it component-wise, right? That's p upper I plus q upper I. And let's see here, scalar multiplication. Of course, we know how to do that too, right? Okay, so it looks a little bit different in the new notation, but that's basically it. Any point, in fact, we can build from the standard basis as well, right? So another thing we should define. We on occasion will need this linear algebra, but so like E lower I in our current notation upper J, this would be Kronecker delta ij. Now what I'm saying is, if you didn't know already, this is 0 if I is not equal to j, and this is 1 if I is equal to j. Now, so for example, the standard basis, let me be a little bit more specific here just for a second. So for example, in R3, we have E1 equal to 1, 0, 0. We have E2 equal to 0, 1, 0. Oops. And E3 is 0, 0, 1. Okay, so perhaps you knew these as I hat, j hat, k hat before, some of you. Anyway, those are your standard basis elements, and you can take any point, say P, and say P1, P2, and P3, and you can rewrite that as P1 times 1, 0, 0, plus P2 times 0, 1, 0, plus P3 times 0, 0, 1. Okay, nothing terribly surprising here. In other words, these standard basis vectors can be used, points. Well, that's the thing, is we can identify points with vectors, right? What is that? So here's I guess this is either a 3-dimensional or an n-dimensional picture, depending on how you look at it. Here's x1, here's x2, here's, well, x3 through xn. So what we're saying when I say point, is it a point, is it a vector? I don't know. I guess that depends on how you want to look at it, right? At least we have that freedom with Rn, because there's this origin there, right? And there's this point P, say out here, right? But on the other hand, there's also this directed vector, right? Like this, which you might call P vector if you were so inclined. And so, is this a point? Is this a vector? I mean, you might do something like angle bracket to emphasize when you're thinking of it as a vector. That's what I do. But mathematically, I could add these things, right? And conceptually, you might say I'm making an identification. Fine, fair enough. But anyway, the point here, of course, is just that we can build any point from the standard basis, and we can either think of the points in Rn as points, or we could think of them as directed line segments from the origin. But that's because the origin is special, right? Let's see here. Now, let's see here. So that's only reasonable, of course, because, again, the origin is, well, the origin. Now, if we're thinking of attaching vectors someplace else, so if I was thinking of attaching vectors at some other point, let me just say out here, and you know, I wanted to attach a vector like that, and say that this point was, gee, I don't know, Q, since I already used P in my picture, right? And this vector here was to say V. Then you'd like to have some kind of idea that encapsulates this. You know, what does it mean to have a vector sitting out here? What if the vector isn't attached to the origin? Well, what we say is that a vector like this that's attached to the point Q and has, you know, vector V. Well, we'd say that this is in the tangent space of Q. So we call that TQ of Rn. That this vector is in TQ of Rn. To be more specific, I need some kind of notation, right? So if I want to talk about that, I could say that vector V, I could just write the point Q specifically, right? And then I can put the vector V second, and I could say, well, that's an element of TQRN. Alternative notation, sometimes you'll see V sub Q as another way to express this. It's the vector V attached to the point Q, okay? So in this language, going back to my original discussion, you might say this. You might say, okay, so I guess what you're telling me then is we make the identification that the origin, that's the origin, fine, the origin, there, is that better? Rn is equal to Rn, and that's essentially the standard identification which is made, is that the vectors at the origin can be identified with the points themselves, all right? But of course, when we attach vectors to some other point Q, well, we can't just make that. It's no longer true that this is just equal to Rn. I mean, there's that Q there. I mean, you really need to keep track of that if you want to be honest to where that vector is. This isn't physics. We can't just move them around. If we want to keep track of where things are, we have to develop a notation for that, and that's this tangent space. So again, this is the tangent space at Q. Now, sometimes you want to think about more than just one tangent space, right? You want to think about all the tangent spaces. And that brings us to what's called the tangent bundle. Eventually, I'll turn the page. So, what is the tangent bundle? Well, so again, let's get back to the tangent space again. I'll use P as I like to. Tangent space at P of, say, Rn. It's, well, I'm saying we can write it like this. It's P comma V, such that, well, V is an element of Rn. I believe in the notes I define it as P Cartesian product with, oh, hi, Mr. Ant. Cartesian product with what? Oh, curses. Rn, yeah. So there's a slight abuse of notation here, all right? So this, again, is the tangent space of P. Then you can also talk about the tangent bundle to Rn, or just TRN, and what that's going to be is the union of all of these guys. So this is a disjoint union. Well, I guess this isn't, but you can look at it as a disjoint union. Anyway, let me not get distracted with technical things. So the tangent bundle is just the collection of all tangent spaces, all right? And again, I should mention in this, when we talk about the vector P comma V, well, what we're talking about is the P is the point of attachment, and then the V is often called the vector part. All right, great. So the tangent space at P to Rn also has the structure of a vector space in a kind of obvious way. So the point P just rides along. So if I wanted to say, you know, P comma V plus P comma W, you just add the vector parts. That's the vector space structure here. If you want to do scalar multiple of a vector attached to the point P, you just scalar multiply the vector part, just like that. So there's your definition of the vector space structure on the tangent space. But there's more than that. There's also, you can define dot product, for example, or you might call it inner product. So let's see, PV dot PW, it's just P, oh, what am I saying? It's a vector, yeah, good job. Duh. No, it's a dot product, so it's a scalar, right? So V dot W, where this is the usual, I mean, if you think of these column vectors, you could write V transpose W if you got linear algebra in the brain, great. And of course, you can also talk about the norm of a vector, the norm of the vector P comma V, or the vector V attached to P if you like. Well, it's just going to be equal to the norm, the length of V itself, right? Or if you prefer, the square root of V dot V. Great. And so once you have a dot product on the tangent space, of course, you can do other things, like you can define orthogonality, right? So, P comma V and P comma W are, oops, I can't spell, orthogonal. Questionable spelling at best. Try that again. Or orthogonal. If V dot W is equal to 0, right? Well, that's great. So then if I have, for example, some set S, some subset S of the tangent space to P of Rn, then I can define the perp. I can say the perp to S is, well, that's going to be P comma V such that what? Well, such that P comma V dot, run out of space here. Let me just write, I guess I'll fit it in. P comma S is equal to 0 for all P comma S in the set S, right? So this is the orthogonal complement to S. Now, so if you think about this, right? If you have some, what we typically apply the tangent space to is you might have a curve, right? And so if the curve is in R2, you've got some, basically you can think of this as being the tangent space to P, right? Now, this wouldn't be the tangent space, I mean, this would be the tangent space to the curve. I don't even have a notation for that yet, but, well, I'll scratch that. So let's say that this is S, right? And then the perp, of course, would just be this thing, right? This would be S perp. That would be the normal line if S is the tangent line. Together, these two things, right, the direct sum of S and S perp, horrible, would be the tangent space to P of R2 in that picture. But of course, the size of the perp very much depends on the where that is, right? So if I had a three-dimensional space, for example, and I had a curve, and if I was so foolish as to try to illustrate it, maybe this is the tangent line, right? S. Here's the point I'm focusing on, P. And then in that case, the perp, right? I guess I should have drawn it in a different line, different color to be more color-coded. There you go. There, I feel better. All right. So in this case, the perp, it'd be a normal plane, right? I mean, it'd be big, well, bigger than the other thing, right? Oh, well, I was trying. It's sad. So there's your S perp. Anyway, so the point here then would be S perp, direct sum with S, right? It's going to give you back the tangent space at P in my picture here, R3. But you see, I could just as well do this picture in Rn. If I did it in Rn, I would have S direct sum S perp. Sorry, I can only bear the color coding for so long. TP Rn. If we're talking about S being the tangent line to a curve, it would still be the case that this is one-dimensional, right? Whereas this would now be n minus one-dimensional. So the size the so-called normal space, because the perp here is what you call the normal space, right? The size of the normal space depends on the ambient context, right? And I could go through the same story, for example, for like a surface, right? If I talked about a surface, here, oh, that's a horrible picture. Oh well. What kind of surface is that? My goodness. If I had a surface in R3, I could talk about a point, and I could talk about the tangent space at that point, right? And then the perp would be the normal line, right? Be the normal line, and in this case, again, you'd have that the tangent space direct sum with the normal line gives you back the tangent space of R3. Not the tangent space of R3. The tangent space, the space of all vectors attached to P. So in other words, what we're calling TPR3 again would be the tangent space to the surface. I haven't given it a name yet. I don't know. Pac-Man. Maybe Pac-Man direct sum. Pac-Man perp. All right, there you go. So Pac-Man perp being the normal line. But this tangent space of TPR3, it's a set of all vectors in R3 attached to the point P. Okay, that's the idea here. I hope I have not been too annoying. It's an important idea though, so we should spend a little bit of time on it. Okay, so that's the tangent vectors at a point. All right. Then the next thing you want to think about, of course, is, well, how about a vector field? Right? What's a vector field? So a vector field would be when we have more than one vector, right? So what's a vector field? Well, I guess you could talk about a vector field along a curve, right? Or you could have a vector field on a surface, right? Of course, they don't have to lie on the surface. They can point out, right? But of course, a vector field is what? I mean, the basic idea is that we attach a vector to each point along some object, right? So essentially, the point here is we say X is a vector field on S. Let's say X such that S and I'll say the tangent may be n-dimensional here for just a second. This would be a vector field on S, and so here S is just generally some object. It could be a curve, it could be a surface, whatever. S is some point set, some subset of Rn, right? So what makes X a vector field is if X of P is where X of P is an element of, well, P direct sum with TP Rn. So, what am I saying there? Not sure I need the TPRN there. I think what I should have is just RN. There's a typo. My notes distracting me. Sorry. So in other words, X of P is actually, this was what we called TPRN altogether, right? In other words, and that has to be true for each P and S. And don't be distracted by the notation. It should be, there's just one, this should be a single X of P, right? At each point in there. Now, you can talk about something called the projection on the tangent bundle. So this is the tangent bundle, right? So what I'm saying is a vector field is a function into the tangent bundle. But it's not just any function to the tangent bundle. The function has to behave a certain way, right? It has to attach a point to each, attach a vector to each point in the object that you're interested in. And so to capture that idea formally, people introduce something called the projection on the tangent bundle. Nothing terribly profound. It's pretty simple. Use a pi. So pi of, say, the point p comma v. There's a typical p comma v is a typical point in the tangent bundle, right? So this projection map, it just strips off the vector part and leaves you back p. And that's true for all pv in TRN. Okay, so if you look at that, then what do we have? We have that pi of, let's say x is a vector field, right? Pi x of p, right? What's it equal to? Well, remember, x of p is a vector in the tangent space at p over n, right? Pi does what? It strips off the vector part and leaves you back the point. So that means that this is p, right? So we take in the point p, we spit back out the point p. That's for all p in S, right? So you can write this as is pi composed with x is equal to the identity on S, if you like. And this makes x a section of, and I think typically people would call it TS. TS is naturally a subset of TRN, whatever. It's a section of a restriction of the tangent bundle to the object of interest, whether it's a curve or a surface or whatever. Just a fancy way of saying you attach one vector to each point in just one vector in the object. All right. But it is nice to have a specific meaning to something being a vector field. It's a section of an appropriate restriction of the tangent bundle. Okay. Anyway, we don't really have much to say about that here. I just mention it in passing. You'll learn more about that in future courses. All right. So I think that's all I have to say about this, my first silly section here. That brings us to tangent and cotangent spaces and bundles, but a little bit more systematic. The next section is actually about some of the about coordinate functions and differentials and our new notation for vectors. So I'm gonna separate the video here, and I'm just gonna stop it here, and I'll pick back up again. It'll still be lecture 2. This is lecture 2 part 1. Next will be lecture 2 part 2.